Welcome to ASA. In this video, we're going to look on areas of surfaces in space. We have a question right here. Find the area of the part of the sphere x squared plus y squared plus z squared equals to 4 squared. This is the equation of a sphere that lies inside the cylinder x minus 2 squared plus y squared is equals to 2 squared. We have a formula for finding the area of surfaces in space. The formula is given by the integral of the square root of 1 plus dz dx squared plus dz dy squared dA. To solve this question, we can either use cylindrical coordinates, spherical coordinates, or Cartesian coordinates. What I'm going to use cylindrical coordinates because they are easy. So I'm going to convert my Cartesian coordinates to polar coordinates. So that means my x is going to become r cos theta, y r sin theta, and from here r squared is equals to x squared plus y squared. Because if we say cos squared theta plus sin squared theta, we're going to get 1 from Pythagoras identity. So from here, if you take the square root on both sides, you can see that r equals to x squared plus y squared. So in multivariable calculus, so if you're given a problem in multivariable calculus, what you have to do, you have to visualize it. So what I'm going to do, I'm going to sketch. So the moment that you have z in your equation, that means you're now in space. So you're in 3-dimensional. So what I'm going to do, I'm going to sketch my x, my y, and my z plane. Okay? So this is what you're going to have. So now you have to look at your equations, right? So you can see here we have x minus 2. So that means the center of the cylinder is no longer at 0 at the origin along the x-axis, right? That means we're going to move 2 units along the x-axis, right? But on y right here, that means y, the center of y coordinate is 0, right, for drawing our cylinder. So let's write here we have z, we have y, and we have x. So let's draw the cylinder, as you can see. So now you can see that the x coordinate has moved from the origin by a factor of 2, right? But for the y, it's still at the origin. Now let's go to the sphere. So for the sphere, we're like, we have x squared right here, which is same as x minus 0, right? So that means the center is 0, and for y it's 0, for z it's 0. And 4 squared, which is 16, so 4 just means the radius of the sphere. So I'm going to draw it. So this is going to be our sphere. So as you can see, the area that we need, it is the part which is inside the cylinder, which is right here. So we need the area of this surface, right? So that's what we're going to find. So now from our formula, we need partial derivatives. So where are we going to get the function, right? So as you can see, we need the surface that we need to calculate is the part of the sphere. So now let's do that. So let's write the equation of the sphere. X squared plus y squared plus z squared equals 4 squared. Let's make this squared start with the formula, right? So now we can make this start with the formula, but if we make this start with the formula, what is going to happen? We're going to have a square root here. And to differentiate, we're going to apply some chain rule, but don't need that. So this is the best way to apply implicit differentiation. I'm going to start by differentiating this respect to x. I'm going to take dx on both sides. So if I do that, you can see if I differentiate here, I'm going to have 2z squared, right? But on the right hand side, 16 is going to become 0 because it's a constant. Same as y is going to become 0 because it's a constant. But on x squared, we're going to have negative 2x. So if we do that, this is what we're going to get. So now we're just going to left with the dividing both sides by 2z. And if we do that, we're going to have negative 2x over 2z. And you can easily cancel 2 and 2. And our answer is going to be negative xz. Let's go to partial z, partial y. Applying implicit differentiation again, we're going to differentiate both sides with respect to y. So if you differentiate z with respect to y, and you have to remember that z is our coefficient, right? It's a power function, it's not a constant, right? You have to take note of that. So I'm going to get 2z is equal to negative 2y. Both 16 and x squared, they're all constant, they're just going to go away. So for y, just going to drop the power, right? Okay, now it's time to divide both sides by 2z, and if we do that, we're going to get 2y over 2z, and if we divide this one, we're going to get negative y over z. Okay, so this is what we have. So now it's a matter of plugging. So let's plug in what we have. So we have negative x over z squared, negative y over z squared. So now you can see if we square negative, we're going to get a positive. So let's rewrite this as 1 plus x squared over z squared, 1 plus y squared over z squared. Okay, so if we apply some reasoning here, so 1 is same as z over z, right? So that means 1 can also be same as z squared over z squared. So the reason why I want to put z squared right here is because I want this to be O over z squared, right? I want to change our denominator to be z squared. Okay, so let's do that. So right here you can see we have z right here, we have z right here, we have z right here. That means you can say all this over z squared, right? It doesn't matter, it's just the same, right? Changing the appearance, but the value still remains the same. As you can see, if we divide here and here, we're going to get 1, which we have right here. Okay, so this is math. Now dividing both sides by z squared. So on the numerator we have x squared plus y squared plus z squared. And like for us, our question has provided us with this information. X squared plus y squared plus z squared is equal to 4 squared, right? So let's put 16 right there. Infinite variable calculus, the square root of 16 is plus or minus 4. And the square root of z squared is plus or minus z. But as you can see, if you look at our diagram, you can see that the surface that we're looking at, it is the upper. So just going to take the positive, right? So it's going to be 4 over z. Okay, so now for z, let's go to our equations, right? Okay, so it said z squared equals 16 minus x squared minus y squared. That means if you take square root on both sides, we're going to have the square root of 16 minus x squared minus y squared. But we want to deal with our problem, we're going to deal with the polar coordinates. So we know that x squared plus y squared is equal to r. So right here, if we factor out a negative, right, we're going to have positive x squared plus positive y squared. So that means we can write this as the square root of 16 minus r squared. And for z, this is what we're going to substitute, right? We have the area as the double integral of 4 over the square root of 16 minus r squared dA. Okay, so now let's apply the limits. So we're going to get the limits. So in math variable calculus, what to get the limits of a surface, what you just need, you need to project or to find the shadow of the surface, right? So if you project the light here, we're going to see that we're going to have a shadow right here, a circular shadow, right? So we're getting the limits from this cylinder. So this cylinder is going to help us to get the limits. So as you can see, our shadow is going to be right here, right, in the xy plane. So that means we have to sketch the xy plane and find the limits, right? So now we have our xy plane. So let's look at our problem. So as you can see, this is the equation of the cylinder. We have x minus 2 squared right here. Okay, so that means the center of x is not 0, right, of the equation. The center of the circle is not 0. It's not centered at 0, 0, right? It's centered at 0, 0 on y, but on x, it's somewhere right here. Okay, so let's draw it. Okay, so if we draw it, you can see this is our circle, right? Okay, and we're going to have y and x, right? So let's just put 1 here and 2 here. Okay, so just put in that 2 here. So now we need to evaluate the limits, right? So you have to be very careful. This is the trick part of this question. Okay, so let's just rewrite it right here. So if we look at this question, we have x squared, x minus 2 squared plus y squared is equals to 2 squared. So let's just expand, right? So if we expand, we're going to say x squared minus 4, which is equal to, we get negative 4 by saying 2 times x, that is x, times the power, right, which is 2 right here. And if we do that, we're going to get negative 4x. And finally, negative 2 squared is going to give us positive 4. So now it's a matter of moving positive 4 to the other side so that it can become negative. If it becomes negative, we're going to have 0 here, and our final answer will be x squared plus y squared minus 4x is equal to 0. But like for us, in polar coordinates, we know this is equal to r squared. Then we know that x is equal to r cos theta when we are in polar coordinates, right? Okay, so we're just going to substitute that, right? Okay, so let's do that. So we're going to have r squared minus 4 r cos squared theta. So let's just expand that bracket by multiplying it by 4. So this is a quadratic equation, right? So what you need to do just to factor out r. So if you factor out r, going to have r minus 4 cos theta is equals to 0, right? And our r is equal to 0, or r minus 4 cos theta equals to 0. So just solving a simple quadratic equation. So let's look at this, right? If we're going to move 4 cos theta on the other side, and it's going to be r is going to be 4 cos theta, right? And that means we have the upper bound and the lower bound of our limits for r, right? 0 is the lower bound, 4 cos theta is the upper bound. But let's go to theta. So to theta, what is going to happen? It is very tricky, right? So you can see, we can agree that this is 0 pi, right? And this is pi upon 2, right? That means that is 90. And if you're going in the anti-clockwise direction, it's going to be negative pi upon 2, right? Okay, but if you're going in the positive direction, this is going to be 3 pi upon 2, or what you can call 270 degrees. So what are the limits? So you can see this is the region of our circle, right? So the region of our circle ranges from negative pi upon 2 to positive pi upon 2, right? If you want to use 3 pi upon 2, you can use, but you have to consider this as your upper bound. Otherwise, you get a negative answer, right? Okay, so let's do that. What I'm going to do, I'm going to take negative pi upon 2 to positive pi upon 2. You can just take pi upon 2 to 3 pi upon 2, just the same. So now that we have our limits, it's time we rewrite our problem, right? Okay, so you can see for dA, that is r dr d theta, and again you have to know that this is the transformation that we use for transforming Cartesian coordinates to polar coordinates. So now this is what we have, but we have a problem right here. What is the problem? We can't just integrate 16 minus r squared, but like for us, here we have r squared and here we have r, so this is the perfect opportunity to use u substitution, right? Okay, so now by putting our limits, this is what we have, and finally r d theta. Okay, so I'm going to let my u be equal to 16 minus r squared. So now it's a matter of differentiating both sides with respect to r. So going to have du dr equals negative 2r. By making dr subject to the formula so that I can substitute it right here, I need du. So I'm going to be left with dr is negative du over 2r. Okay, so now I'm going to put it right there. Okay, so you can see for dr, what you have put du over 2r. And you have to take note that this negative sign, since the constant, I just put it right here. Okay, and right here you can see if we say 4, 2 into 2 is going to be 1, 2 into 4 is going to be 2, right? R and R will get away, and now I have my clean u, right? Okay, so this is what we're going to have, right? But you have to know that if we say root u is same as u to the power 1/2, right? And by laws of indices, if we want to raise something, that means we're going to say u to the power negative 1/2, right? It's also basic integration. You're just going to add 1 to the power and divide by the new power, right? But you have to take note that negative 2 divided by 1/2, that is 4, right? And 1 minus 1/2 right here is going to be positive 1/2. So let's simplify it like this. Okay, so now it's a matter of saying upper bound minus lower bound, but before doing that, we have u, and u is 16 minus r cos squared theta, right? So there's no need to rush here. Okay, so now let's put our u 16 minus r squared cos theta, right? Okay, so you have to know some identities when solving this type of questions. You have to know some Pythagoras identities, right? Okay, so this is what we're going to have: upper bound minus lower bound, right? Remember, for upper bound we have r squared, which is 4 cos squared theta. So if we say 4 squared, we're going to have 16. If you say cos squared theta, we're going to have cos squared theta, right? Okay, and finally the lower bound is 0, so r is just going to die, and we're going to be left with 16. Okay, and from here you can see the square root of 16 is 4, right? Okay, so now what identities are we going to use? So we're going to use sin squared theta plus cos squared theta is equals to 1. So since we have cos squared theta right here, what I'm going to do, I'm going to make sin squared theta subject with the formula, right? Okay, so if you make cos squared theta subject with the formula, you can see that sin squared theta equals to 1 minus cos squared theta, right? Okay, so I'm going to look at it, just keep it in mind, right? So from here, what I'm going to do, I'm going to factor out 16, right? So you can factor out 16, right? You can see we have 16 and we have 16, just simple factorization. Okay, so let's do that. If we do that, you can see, but by the set form, if you have solved any problem solved in set form, you can see you can take the individual square root of each component as long as we have a multiplication sign right here. So the square root of 4 is equal to 4, right? So that means we're going to have 4 here, and 16 is going to go away. But remember, we have 4 here and we have 4 here, so you can just factor out, right, and factorize. But also we have 4 here, so we're going to multiply by the 4 we have factored out, right? So we're going to have negative 16. Inside the square root is going to be 1 minus cos squared theta minus 1 d theta. So now for 1 minus cos squared theta, we have our identity, which is right here. So I'm just going to put sin squared theta, right? Okay, so the square root of sin squared theta, this is simple, it's sin theta, and we have our 16, right? So now it's a matter of integrating sin theta and 1, right? But we have a negative, right? So in most cases you may forget to include this negative, so it's just better if you see an opportunity to get rid of it, you just get rid of it. So I'm going to multiply this by the negative, and I'm going to multiply this by the negative, and evidently 1 is going to become positive and sin theta is going to become negative. Okay, so now let's integrate. 1 is going to become theta, and for sin theta we're going to have negative cos theta, right? But we also have this negative, so negative and negative, that we yield a positive, and still for our limits, upper bound and lower bound. So if you have 3 pi upon 2 and pi upon 2 is still good, right? Or obtain the same answer. So now let's say upper bound minus lower bound. So this is what we're going to do, substituting pi upon 2 on the upper bound and negative pi upon 2 on the lower bound. If you do that, you're going to get your answer as 16 pi. So thank you for watching. Don't forget to subscribe, right?